So in this example, let's quickly have a look and see what we should substitute for. Scanning through it, we see that there's this logarithm of u that appears, and the derivative of the logarithm of u is 1 over u, and that also appears as a factor in the integrand. So perhaps we should substitute for the logarithm of u in terms of w. I'm using w since the variable u is already being used. So dw is 1 over u du, and therefore our integrand simplifies down to 1 over w squared, because I'm replacing logarithm of u with w, and the du over u gets replaced with dw. So our original integrand, we've simplified it through this substitution down to something easier to deal with. And that's the goal of this substitution, is to take a complicated integral and try to reduce it down to a simpler one that you know how to deal with. And in this case, now we can compute the antiderivative. This is negative 1 over w plus our constant of integration c, which is then negative 1 over ln of u plus c. So there's our result. How about the next example? What do you think we should substitute for? So have a look through the integrand. See if you can spot something, piece of the integrand where the derivative appears as a factor. And so if we look at the argument of the sign, pi by v, and I'll look at u equals pi by v, then the derivative is negative pi by v squared dv. And this dv by v squared appears in the integrand. And so this seems like a good choice, because if we take u to be this function, then the derivative also appears as a factor. Notice I'm not too worried about constants, because I can always move constants outside of an integral. So in this case, we can rewrite it like this by moving the constant over next to the du, and so our integrand then simplifies down to sine of u. The dv by v squared gets replaced with negative 1 over pi du, so this is negative 1 over pi, which can come out, du, and so our integrand is now just the sine function. And the integral of sine is negative cos. And now I can replace u in terms of v, negative 1 over pi cos pi by v, plus our constant of integration c. Okay, in this last example, again, let's scan through it and see if we can find something which we can replace where the derivative of that thing is appearing as a factor in the integrand. And hopefully by doing that substitution, we can simplify the integrand down to something that's easier to deal with. And sometimes it can start to get tricky. I mean, what should I replace? Should I replace the whole thing on the bottom, the square root? Well, if we replace the whole square root on the bottom, the derivative of the square root would be related to dz over the square root. Okay, so that would probably take care of all of this stuff, but the problem is then we have this z squared that we need to rewrite in terms of the new variable we're substituting for, because we need to take the entire integrand and replace it, all occurrences with the variable z in this case, with the new variable, let's call it u. So oftentimes you just try something and see if it works. If it doesn't, go back to the drawing board. In this case, I'm going to take a bit more modest approach. I'm going to say, well, I'm going to be content with having a square root in the bottom, but I do really want to get rid of the 1 minus z inside the square root, because if I could replace that with just a single variable, my life might be a little bit easier in terms of dealing with that denominator. Okay, so when we do this substitution, the thing under the root sign gets replaced by a u, the dz gets replaced by a du, negative du in fact. The only thing that's left is this z squared on top, which we need to get rid of. But we can go, switch colors for this, we can go and look at the relationship between our old variable and our new variable and recognize then that, well, then z has to be 1 minus u. And what that means is I have a way of replacing every occurrence of z by something involving u. So in the denominator there's a root u downstairs. The dz gets replaced with a negative du. I'm going to put the negative out front. So I'll put that negative out front and then just write the du at the end. The z squared I can replace with a 1 minus u all squared. Okay. At this point, sometimes it's hard to see if you actually did simplify the problem and make it easier to work out what the integral is. In this case, if we imagine now expanding out the numerator and then dividing the root u into each term, then we've just got a bunch of powers of u added together, and we know how to deal with powers of a single variable u. So let's do that. Let's expand out the numerator. 1 minus 2u plus u squared divided by root u du. So I can divide root u into every piece. So into the first piece, I can just write it as u to the negative 1/2. U divided by root u, that's just root u, or u to the 1/2. And root u going into u squared, that would be u to the 3/2. So it would be 2 minus 1/2, or 4/2 minus 1/2, which is 3/2. And now we can compute each of these antiderivatives just by using a power rule. So u to the negative 1/2, that's u to the 1/2 times 2, that's the antiderivative of that. The antiderivative of u to the 1/2, well, there's a u to the 3/2 is which the exponent should be when you compute the antiderivative. And then what do we have? We have a 4/3 negative adjustment, so that when we do take the derivative, the 3/2 comes down. A bunch of canceling happens when you multiply 3/2 to 4/3 and leaves you with a negative 2 there. And the last one, the exponent should be 5/2, and there should be 2/5 as the coefficient out front, plus our arbitrary constant of integration. And so there we've computed the antiderivatives. Now we just need to rewrite everything back in terms of our original variable. And this would be then 2, 1 minus z to the 1/2 minus 4/3, 1 minus z to the 3/2 plus 2/5, 1 minus z to the 5/2, and then plus our arbitrary constant of integration. And so there's our antiderivative. Yeah, it looks kind of complicated, but as we can see, the way we got to it was looking at the integrand, trying to simplify it in terms of another variable through a substitution. We got it down to an integral of a bunch of powers of u, which we could then compute and then put back in terms of the original variable. Okay, so these last few examples are to illustrate, and so these last 6, I guess, examples are to illustrate the way we apply a substitution. Try to find something in the integrand where its derivative also appears and get rid of them in hopes that we can get an integrand that's simpler and easier to work out.